question 2a. So the air in a kitchen has pressure of 1.0 into 10 to the power 5 pascals and temperature 22 degrees per Celsius. A refrigerator of internal volume 0.36 meter cube is installed in the kitchen. With the door open, the air in the refrigerator is initially at the same temperature and pressure as the air in the kitchen. Calculate the number of molecules of air in the refrigerator. So to solve this question, we will use the ideal gas law. So that is PV is equal to nRT. So P is the pressure, V is volume, N is the number of atoms, R is the gas constant, and T is temperature. But since in the question they're asking us to calculate the number of moles, we will be swapping the R for K, and K is the Boltzmann constant, so you can find this in your data booklet as well. It's 1.38 into 10 to the power of negative 23. So you will rearrange the formula for N and replace the gas constant with the Boltzmann's constant and just substitute the values we have. So 1.0 into 10 to the power of 5 multiplied by 0.36 divided by 1.38 into 10 to the power of negative 3, and you will get 8.8 into 10 to the power of 24. And that's how you solve 2a. Part B, the refrigerator door is closed. The air in the refrigerator is cooled to 5.0 degrees per Celsius and the number of air molecules in the refrigerator stays the same. Determine the pressure of the air inside the refrigerator. So we need to keep in mind that we must convert the Celsius to Kelvin. And to do that, we have to add 273 to the Celsius. So in part A, in the question we got 22 degrees Celsius. So we will plus 273 and we will get 295 Kelvin. So we will use the formula over here as shown. So this is not in the data booklet, but it's something you should know. So this is pressure 1 over temperature 1, and pressure is equal to pressure 2 over temperature 2. So the first pressure we have is 1 to 10 to the power 5, and we have 295 Kelvin. So 273 plus 22 will give you 295 Kelvin, multiplied by, so we are in the question they're asking us to find the pressure, so the second pressure. So we're going to move this the second temperature to the other side. So this will be multiplied by whatever value we have here. So T2 will be equal to 273 plus 5, as they're given us the second temperature right here. So when you solve for these values, you should get this value right here, 94237 point all that, and you'll have to divide that by 10,000, because as you can see it's 1 into 10 to the power of 5 here, which is why you have to divide it by 10,000. And when you do that, you will receive 9.4 into 10 to the power of 4 pascals, and that's how we solve part B1. As for the second part, the door of the refrigerator has an area of 0.72 meters square. Show that the minimum force needed to open the refrigerator door is about 4 kilonewton. So so the formula we'll be using is P is equal to F into F over A. So we'll rearrange the formula for F, as F is equal to delta P into the area. So delta P is basically the first pressure 1 minus pressure 2. So over here we have the two pressures here. So basically you'll do 1, subtract the 0.94, because 0.94 because this is into 10 to the power 5 with 10 to the power 4. So it's into the power 5, you'll have 0.94, and you'll multiply that into 10 to the power 5, and this will be equal to 4,320, which you'll have to divide by 1,000, and you will get 4.3 into 10 to the power 3. And that's how you solve part 2. And as for part 3, it asks us to comment on the magnitude of the force in P2. So this was taken from the Marx scheme. I mean, the force is a the force here is very large over here, and see, like, door of the refrigerator has an area. Yeah, so the refrigerator door is closed, so there must be a mechanism that can lower the force. So that's basically two answers that's needed here. That's how you solve question 2.